Okay, so hi everyone, and thanks for joining for the season finale. So for the last talk of this year's seminars, we have the pleasure of hosting Dr. Stella Boula. So let me say a few things, a few words about Stella. So Stella was born in Chios, in the Aegean Sea in Greece, and then she moved to Athens to study physics and astrophysics, where she also did her PhD. And then since 2021, is that right, Stella? She is in Poland, in Krakow, at the Institute of Nuclear Physics at the Polish Academy of Sciences. So her field is, Stella works in high energy astrophysics, and today she promised to talk both about blazars and galaxy clusters in one talk. So we look forward to that, Stella. And thanks again for accepting our invitation in short notice. So please go ahead.
Thank you a lot for the intro, and I'm very glad that even in that way I can see you, and I hope that we will meet in person next year. I hope that I will present a very good connection between these two different objects, blazars and galaxy clusters. The main line is the cosmic accelerators. So let's start this complicated path. My outline here, first of all, cosmic accelerators, why we want to learn more about them. Then we will talk about AGN and blazars, the radiation models that we are using in order to explain the emission that we can detect of these sources, then how we can apply them, and the particle acceleration, why it is important, and how we can apply the to the galaxy clusters our theories. So here, first of all, because we will talk about many topics that take home messages and where you should stay focused and pay attention. How we can explain the multi-wavelength emission of blazars by minimizing the number of free parameters. Now we are very lucky because we are living in an era that we have multi-wavelength campaigns, we have monitoring programs, we have the multi-messenger astronomy, so we can find the correlations between photons and particles, but at the same time, we need to avoid the cooking method that we can use many parameters in order to explain what we're getting from these sources. And it's how we will go to the role of the mass accretion rate and how can explain the statistics that we have from blazars. Then in the second part, we will focus on particle acceleration, and we will see the mechanism that can possibly give a solution to the injection problem, which I will not spoil it from now, but I will explain you later what exactly is. And please, if you have questions, just ask me, because maybe at the end, everything will be a mess with all this info. So first of all, who is responsible for the non-thermal emission? Here you can see the particle distribution. So we can have a small friction of the non-thermal particles, which means that what is a non-thermal particle? It is when we have a distribution that is going to the velocities close to the speed of the light for the particles. And we have many astrophysical sources that we can detect non-thermal emission from supernova, X-ray binaries, neutron stars, active galaxies, GRBs, FRBs, galaxy clusters. So our universe, it is full of cosmic accelerators and natural labs that allow us to study these processes. And you can see here the thermal distribution where the non-thermal fraction is small, and we're going to power law for the particles, and then it is large. So we want to check how the particles can be accelerated in these energies. The first topic that we want to discuss today is about blazars, and blazars is a subcategory of active galactic nuclei. Here you can see a very nice sketch from the Science Communication Lab of DESI. The supermassive black hole here in the center, the accretion disk around, the environment with the clouds, the strong relativistic jet, where in the case of blazars, it is looking toward the observers. And we can see strong variability, the emission, it is, the luminosities are very high. And we can see also strong polarized signatures. And these labs are very good for the high energy astrophysics. And here you can see how the mass accretion rate can play a key role in the luminosity of these sources. AGNs can be divided into categories, radio quiet and radio loud. Radio quiet AGNs are the 90% of these objects, and radio light the 10%. And we have two main subcategories, the flat spectrum radio quasars, which are higher in the luminosity, and BLAC objects. And also in AGNs, we can have strong and weak jets. And also the accretion disk is important in the emission. When we have a radiatively efficient disk, then the sources are more luminous compared to the radiatively inefficient disks. So let's go to blazars again. What we have is the supermassive black hole, the strong relativistic jet, which is looking toward the Earth. And these cosmic accelerators, they can accelerate particles, cosmic rays, as you can see here, and neutrinos. We have evidences for neutrinos that are coming from blazars, and of course, photons. And the question is where these photons are produced. We don't know exactly where inside the jet, but in the case of blazars, we have these characteristic components that we can detect, one in low frequencies and one in higher frequencies. In the case of flat spectrum radio quasars, FSRQs, we have a strong UV signature because of the efficient radiation accretion disk. In the case of BLACs, this disk, it is inefficient, so we cannot see this UV signature here. And in the emission, we should take into account the population of the particles that can contribute to the light that we can detect. So when we study the electrons, then we are talking about leptonic models. But when we study electrons and protons, we are talking about leptohadronic models, and then we are able also to study cosmic rays and neutrino production. But in this talk, we will focus only in the leptonic scenario. So here you can see again the spectral length distribution. The low frequency component is related to synchrotron radiation because we have the existence of magnetic fields, so the electrons can interact, and then we can have from radio to X-rays. And the higher frequency component is related to inverse quantum scattering. The electrons can interact with low frequency photons. So in that case, maybe synchrotron photons can be target or photons from the environment, and we can have this characteristic band. When we want to study the spectral distribution and we want to model these sources, we need to solve the kinetic equations of electrons and photons. So what are these equations is how the number density or the number of electrons and photons, can change in the time, how they gain and they lose energy if we have injection of particles into the source. And here you can see the leptonic processes that we can take into account. And because these equations are integer differential and they are coupled, in most of the cases, we cannot solve them analytically. That's why we need to have numerical codes in order to solve self-consistently the spectral length distribution. And in most of the cases, when we want to assume the geometry of the source, we think that this is a constant blob of plasma, for example, a spherical blob. But in the last years, this is changing also, and we can have new numerical approaches like ours, one zone expanding model. So we're taking again into account the leptonic processes in the emission, but now in an expanding source. So now we assume that the radius of the blob, it increases by the time. And here you can see how these two characteristic bumps changes in the time, depending on the assumptions that we can do about the magnetic field, the electron luminosity, and how the peaks, for example, of the components shift to lower energies. And an important thing is this peak here, which is related to the synchrotron self-absorption. Here we have a break. And this is a problem when we want to explain the multi-wavelength emission from radio to gamma rays in these sources, because radio photons are absorbed, and we need to have larger regions in order the radio photons can escape and be detected from us. And here you can see this standard Z model. The high energies are produced close to the central engine, and as we are going toward the Z and the sources is larger, then the radio emission can be produced in higher distances from the central black hole. And now that we have a numerical tool, we can see if we can reproduce a continuous set. So what we assume here is that a blob of plasma is created close to the central engine. Here it is optically thick, this region. We cannot detect radio photons, but as this blob moves inside the Z, at the same time, it expands. And if we assume that we have many blobs of plasma that we have into the Z, then we can integrate the flux from all these blobs, and we can calculate the total spectral distribution. So we need to have an assumption about the radius. For example, here we assume that we have a constant expansion velocity, and the radius increases linearly by the time. We need to say something about the magnetic field and the electron power, which can be related to the dynamics of the Z with these indices here, S and He. And we will solve the kinetic equation, and now we will take also into account expansion of the source. And in that case, we can calculate and compare with observations, and as you can see, this can work, and we can find a way, actually, we can find where these radio photons are produced and localize this emission. And this tool can help us also to flaring episodes, because blazars are characterized by strong variability. So maybe we can have a more energetic blob that is created inside the Z. And this can be because we have a higher mass accretion rate. This is not necessary to be constant. And in that case, the emission of this blob can be detected as a flare, because it can produce photons which would be above the steady state condition. Or the blobs can be created into the Z, and as they're moving inside, they can, as we have the expansion, we can have a reacceleration episode for a reason, maybe because a shock happened, maybe because we have an amplification of the magnetic field. We don't care now what is the reason for this reacceleration episode, but if we have it, and depending on where exactly we are into the Z, we can detect flare in photons. If we are close to the central engine, then because it will be in the optically thick region, we will not be able to see anything in radio photons. But if we are further, then we might see a characteristic flare in high energies and low energies as well. And we applied this model to Markarian 421 2013 flare that it was detected. And we assume that we have an energetic blob, and close to the black hole, we have a reacceleration episode, which is described by a Lorentzian distribution for the electrons. And then the gamma rays can be explained. Also, you can see here more flares. Of course, if we have more blobs or more episodes, we can explain these flares. And because we were in the optically thick region, nothing was detected exactly at the radio frequencies. But in later times, 60 days later, and because this blob is energetic enough, can explain from the transition of the optically thick to the optically thin region, the flare in radio frequencies which was detected. So here we have a connection between different wavelengths by assuming one thing and not put a lot of pre-parameters in our problem. And okay, this was for a BLAC object, but what is happening also with the flat spectrum radio quasars, where the external photon fields are important because we have the radiatively efficient disks, and here we can assume different external photon fields like accretion disk photons, photons from the broadline regions, from the torus, from synchrotron emissions from other regions of the jets, and an alternative scenario that we introduced a few years ago, photons that are coming from the accretion disk and they can be scattered up to the particles of the accretion disk winds. And of course, also the sources created self-synchrotron photons, which can also interact with the particles. So now we want to check the statistics of the blazars. So we will go back to a constant blob, the expansion velocity is 0, and we want to check the properties of these objects. So when we want to fit an SED, we need to define the basic parameters of electronic model, which is the magnetic field strength, the electron's luminosity, the electron distribution, if we assume a pre-accelerated particle distribution with a power law, with a broken power law, if we let the system involve itself and have a particle acceleration. Also, we need to define the energy density of the external photon fields, the bulk Lorentz factor, because these blobs moves relativistically inside the jet, and the Doppler factor, which has to do with the viewing angle between the observer and the axis of the jet. So the first 4 points can be related to the mass accretion rate. And here you can see our model. We have the accretion disk photons here. We have the wind particles here. These can be scattered and we can create an isotropic photon field which interacts with the particles inside the blob. And in that way, we can reproduce a theoretical blazar sequence. So the blazar sequence was introduced by Fossati et al. In 1998, and they found a trend from flat spectrum radio quasars to BLAC objects. Flat spectrum radio quasars are more luminous compared to BLAC, and also the peaks of the components are in lower frequencies compared to the in FSRQs compared to the BLAC objects. And here, by changing only one parameter, the mass accretion rate, we are able to explain the statistics of blazars. And here you can see with 2 orders of magnitude difference in the mass accretion rate, how we can cover all the plane. And also we use 2 different values for the supermassive black hole. So you can see that the difference is not such important. It is almost in the same area, and the mass accretion rate is something that can explain these statistics. And also we have more observational trends to support the statistics of the blazar sequence. For example, sorry, I didn't explain you here what it was, I'm sorry. So here we have the synchrotron peak frequency, and this is the photon index in gamma rays from the Fermi Gamma Ray Telescope, and this is the statistics that we have from 1,000 blazars, and you can see this trend here. And also we have more observational data, or for example, the peak of the Compton frequency, again, the photon index in gamma rays, the luminosity in gamma rays, and the photon index in gamma rays. And as you can see, there is a trend from FSRQs to BLX, and here the same, FSRQs are more luminous in gamma rays, and we can explain them with our theoretical sequence. And also here the Compton dominance, which is the ratio between the peak luminosity of Compton to the peak luminosity in synchrotron component. And you can see this behavior here. But what I didn't tell you it is that we assume that we have a broken power law in the particle distribution in order to explain and have this shape of our spectral distribution. And okay, the break, it is depending on the mass accretion rate, but it is an ad hoc hypothesis. What exactly is the index of the particle distribution? In all the cases, it remains constant, but we didn't use any physical approach to explain why it should have the specific values that we are using. It was motivated by the observations. And that's why we wanted to check how the particle acceleration can play the role to give us the right distribution for the particles. And now we don't have anymore an injection term for the electrons, but we have this acceleration time scale here, which allows us to give energy to the particles according to the first order Fermi acceleration. And we find the connection between the mass accretion rate and how it changes for the acceleration time scale. So it is almost linear here. And we have the dependence of the mass accretion rate and the energy of the particles. And in that case, we have the model where we have the acceleration zone and the particles can be accelerated here. Then are injected in the larger volume. This is the cooling zone. And in the case of BLAC objects, the cooling zone is not important because we don't have external photon fields. But in the case of flat spectrum radio quasars, this cooling zone is very important and can play a key role on the gamma ray emission. So here you can see the spectral distribution that we can calculate. This is the acceleration zone for the BLX, and this is the cooling zone. You can see that the acceleration zone is more dominant. But in the case of flat spectrum radio quasars, the acceleration zone can explain the low frequencies, but the higher energies can be explained by the cooling zone, which is more important. And again, we can reproduce a theoretical blazar sequence which has all the characteristics that are in agreement with the observations. And also we can apply this model to individual sources, like here in 3C273, we zoom here in the high frequencies. And you can see that the acceleration zone, for example, can explain the X-rays, but the gamma rays here, these are the limits of the Fermi Gamma Ray Telescope, can be explained by the cooling zone. So that was the story about the blazars. And if you have questions about this part, please let me know. Okay. So should I continue to the next? I hope that I don't speak very fast and you're able to follow me because there are many topics. Okay, I'm still here, right? You can hear me.
Yes, everyone is here.
Okay. I'm moving to the next part, which is something that I'm doing right now. The first part, it was something that I did during my PhD studies. Now this is what I'm working on now, and it has to do with the particle acceleration and galaxy clusters. So first of all, again, because when we want to study these objects, we need to have numerical methods. It is very important. We cannot solve analytically the problems and see the behavior in different scales. And depending on what we want exactly to study, we can have different types of codes that they can help us. For example, when we are focusing in macroscopic scales, we need to have MHD codes, but when we want to check how the particles are accelerated, we need to go to the kinetic scales. And this means that we need to have particle in cell simulations, and I will explain you in a while how we are doing that. But at the same time, sometimes we need to fill the gap between the kinetic scales and the macroscopic scales. So for this reason, we are using hybrid codes, which can take into account also the MHD and the kinetic scales. And here is a very busy plot with a lot of info. But what I want you to keep in mind is the sizes of these sources here and the time scales that the phenomenon are happening. So here in this yellow region, we have the magnetohydrodynamics codes. We have the MHD codes. Here, ions and electrons are simulated as fluid. We don't care about the kinetic processes, so we cannot say something for the particle acceleration. This is the best when we want to study large scales in our problems, for example, the dynamics of jets. And in general, the good thing with these codes is that they are not computationally expensive. So we can do many simulations. We can also, okay, of course, they're not expensive compared to other codes because many simulations in MHD can be computationally expensive. But in general, because they don't care about the kinetic scales, these simulations are not such heavy as in the case of, for example, hybrid codes. In hybrid codes, we can fill the gap between the two scales. So the ions are particles, and then we want to study the kinetic effects and the scales. The electrons are massless fluids, so here we have the MHD approach, and the plasma should be quasi-neutral, and we don't care about the electron scales when we study this, when we are using these codes. It is the best when we want to check the physics of the ion scale processes. And also the computational cost is not such high. It is better, for example, compared to the peak simulations, where in the peak simulations, both electrons and ions are particles. So we don't have assumptions about the plasma. And this is very helpful when we want also to study electron scales and see how the electrons are evolving into the system. But because we need to do a lot of calculations, and of course, our simulation boxes are very big, this it is very high in computational cost. And let's see how exactly the peak simulations are working. And this is a method that is also is used in hybrid codes. So the important thing is that we have the Lorentz force. We have the particles with specific position and velocity. And then we can use weighting functions. We can calculate from the distributions to the density and the current. Then we can integrate and go and calculate the electric and the magnetic fields, and again, the Lorentz forces. So we can have a loop which continues, and then we can study these systems. You can imagine that we have a box, or simulation box. It has grids, and in each grid we have a number of particles. These are macroparticles, so it's not, for example, the real particles. We don't have, again, the opportunity to do this. It needs a lot of computational power, but even in that way, it allows us to study this system. And here is a generalized hybrid code, which is developed by our collaborator, Takanova Mano, which is something maybe a bit because it is generalized, something new. The energetic particle population interacting self-consciously with MHD fluid. This is something that in general it happens in hybrid codes. But the good thing is that we can take arbitrary species of the particles. So we can have ions, but we can have also other population of particles, and the same for the fluids. But in general, in the simulations that I will show you, I'm using ions as the kinetic species and electrons as a fluid. And then again, we can calculate everything by MHD and kinetic processes for the ions and see how our system evolves in time. Okay, and why we need all these tools? These tools can be applied to many sources. They can apply in all cosmic accelerators. But here we will focus on the galaxy clusters and the shocks that are happening in merging. And at the end, what we want to answer is the electron injection at these shocks. So here you can see a picture from Nature Astronomy. We can zoom in this area here. We have the cluster merger shock. Here we have these radio relics that we can observe in X-rays and radio. You can see the direction to the cluster center. And this environment in general is very rich. For example, here you can see an active galaxy, the radio jet of this galaxy. And we want to see how electrons can be accelerated there. Here is the radio map. And from the observations, we can say that we have supersonic flows and we have baryonic matter, and we have large scales of structures, and these shocks can interact with the hot in the intracluster medium and the plasma beta. Okay, let me show you the definitions of the plasma beta, which is the ratio of the thermal pressure to the magnetic pressure. It is high. That means that we have low values of the magnetic field strength. For example, it is close to microgauss. And we want to see how these shocks behave. As I said, we can observe it in radio and X-rays. They are called as radio relics. The Mach numbers are low compared, for example, to other cosmic accelerators. The Mach numbers are defined by the shock speed to the alphenic speed, for example, for the alphenic Mach number, or for the sonic Mach number to the sound of the speed, to the speed of the sound, sorry. And in these cases, we can have diffusive shock acceleration, which seems to be important in general for the shock acceleration. But there is a problem. And this problem is the electron injection in these sources. We need to have pre-accelerated electrons. From the radio and X-rays, we know that we have a non-thermal population. You can see it in this part here, radio X-ray, and exactly the same. It has to do with the shock. This is the case of the diffusive shock acceleration, this picture here, or Fermi acceleration. What we want here is that the particles can go from the one side of the shock to the other, back and front, and they can gain energy in that way. But at the beginning, we have a thermal distribution here, which can be described by a Maxwellian. Here is the energy that we need in order to be able, the particles to go back and front from the shock layer. And we need to have energy in this gap here, because the particles at the beginning, they can move according to their Larmor radius. Sometimes this shocks, the layer is larger of this Larmor radius. So if the particles are trapped here, they will never have enough energy to go and do the diffusive shock acceleration back and front. So they need to reach this minimum value, this threshold here, to be able to participate to the Fermi acceleration. So from the thermal distribution, how we can accelerate particles and can be the electrons and can be injected here in the Fermi acceleration. This is the injection problem. And this is what I will try to explain in the next slides, how we can solve it. So now we will focus on shocks and specifically to quasi-perpendicular shocks. What are these? So here we have a structure of a shock. This is the upstream medium. This is the shock, and we have the overshoot here, and this is the downstream. This is the shock normal, this arrow here. And we have also a magnetic field. The angle between the magnetic field and the shock normal defines if we will have a quasi-perpendicular shock, a perpendicular, parallel, quasi-parallel. How? If this equals to 0, then we have a parallel shock. If it is below 45 degrees, it is a quasi-parallel shock. If it is above 45 degrees, it is a quasi-perpendicular shock, and in 90 degrees, it's a perpendicular shock. So the electron injection, it seems to be effective mainly in quasi-perpendicular shocks. And what are the key elements when we want to study these sources is the particle reflection in the shock ramp here. Due to the magnetic mirror forces, this can play a very important role, as we will see. And the particles can gain energy because we have motional electric field in the upstream region, and this is the shock drift acceleration or the shock surfing acceleration or particle wave interactions. We will see examples in a while, so I hope that you will not have questions. What exactly are these? And also, the electrons can be trapped here near the shock by scattering in upstream waves, electromagnetic waves that we can have. And in that case, they can participate in multiple circles for shock drift acceleration or shock surfing acceleration. And if the particles remain here, then they can gain energy in time, which is important because if the energy that they will gain, it is more than the energy that we need to go to the diffusing shock acceleration, then this process is successful. And when we want to study shock acceleration, we need to go to the micro instabilities of the kinetic scales that they can be produced, because then we can have generation of waves. We can have self-generated waves in the upstream medium, and with the wave-particle interactions, then the particles can gain energy. And in general, when we want to study the parameter phase space in the shocks, we need to check all these parameters here. So if we want to cover everything, we need to do simulations for all these parameters here, which it is expensive, computational, of course. So previous works that have shown how the electrons can gain energy, and they can explain the electron injection to the shocks. So let's focus here in this plot, and I will explain you what we need to see. So with blue color, we have the earlier time steps, with red color, the later. This is the shock here with this line, it is the shock layer. This is the upstream medium, and this small part here, it is the downstream medium. So the particle is coming, it is moving here, and it is trapped somehow in the shock, and because of the shock drift acceleration, it gains energy. And suddenly, because we have reflected from the shock, it is going back to the upstream. This is the story of the particle, and also you can see it in this plot B here, where the particle is coming upstream. This is the Z axis, so it moves, and this in x-axis is the position minus the position of the shock. That's why in 0 we have it is constant because it moves with the shock, and then it is going back upstream. And let's go now to A, to the figure A. This is the energy, and this is the position in the shock. So you can see it here, the particle, it is upstream. When it is going to the shock, it gains a significant amount of energy, as you can see here, and then it is going back upstream. So this can work at subluminal shocks. What are the subluminal shocks? In general, when we study these shocks, we are going to another frame, the Hofmann-Teller frame, which can describe the upstream plasma in parallel to the magnetic field. And in that case, the motional electric field, it vanishes. So it helps us to study the shock, because then the upstream flow, it is parallel to the shock normal. And we can see, when the velocity of this frame, it is smaller than the speed of the light, then we are talking about the subluminal shock. If it is larger, we cannot find Hofmann-Teller frame. Here you can see that the acceleration time, it is more or less equal to the ion cyclotron frequency, and how we can calculate the energy gain of these particles. And in other works, you can see also that the particles can also participate in multiple shock drift acceleration circles. So what we have here is that the particle is coming. Okay, let's go here in the energy. So it is in upstream. Here is how it gains energy by the shock drift acceleration. The energy remains constant, but then we have a new circle, so the particle can gain more energy. And why we can have multiple circles? Because we have the reflection of the electrons up to self-generated electromagnetic waves, which help to the particles to be injected again to the shock drift acceleration. And this give us the upstream power loss spectrum, and also for the downstream. It seems to be more effective for higher beta. And the main question is if the maximum energy that we can reach from these multiple circles, if it can be larger of the energy that we need to go to diffusive shock acceleration. And in our group, they did the work in order to check this behavior, and they found that these shocks can show ripples here. The ripples in the shocks are well known from many years, but this was a study with specific parameters. And here, these ripples can be related to the alpha ion cyclotron instabilities and mirror instabilities. I will explain you in a while what exactly are these. And also we can see shorter scales from the electrons, as you can see in these figures here. But the most important thing is that you can see particles. For example, the red guy here, it's going to the shock, so it gains energy and then it remains constant, and how they can gain energy. And if we analyze these particles, we can see that there is strong phase angle scattering. You can see from these arcs here in this phase, in this momentum space. And this is an evidence for the stochastic shock drift acceleration, which was introduced in 2019. So it is something new in general. Here is the shock layer. And inside here, we can have this stochastic phase angle scattering because of the waves. And the particles, the electrons, can gain energy. And if they gain enough energy to above the threshold for the injection to DSA process, then they can go under the DSA and gain more energies and explain the observations that we have. And this is SSDA process. Also, it is appeared in Earth bow shocks in these simulations here, in simulations that people do again with peak, with other parameters the last years, in hybrid simulations. And in hybrid simulations, we cannot have electrons, but we can calculate the fields depending on the ion scales, and then we test the particle to see exactly how the electrons are behaving. So this was work from Rothenbergis in 2019, and they had the same behavior. But this was in plasma beta equals to 1. Here we have plasma beta equals to 5, so it is larger. And these ripples also depends on the plasma beta. So when we have higher values of it, then the ripples can have larger scales. And this is important because this rippling seems to be related to alpha ion cyclotron instability. And we need to explore this space and see how we can take the particle acceleration in higher beta. But when we need to explore the plasma beta, that means that we need a lot of computational power in order to do the peak simulations. And then we have a solution because we have the hybrid simulation. So we can use them and see if we can have an estimation about the ripples in higher beta or in general for different parameters. And why we want to do this? This is the work that I'm doing now. It is to find the critical Mach number to trigger this instability and see the role for the shock surface rippling. What is the shock Mach number, the critical shock Mach number, sorry. It has to do with the ion reflection. So we have an incoming beam and these particles can be also reflected in the shock layer. And these, when we are above a critical value, then we can have upstream wave generation. And in the case of the alpha ion cyclotron instabilities, then the ion cyclotron frequency, it is more or less the same with the alpha frequency. Then the plasma can be unstable and we can have electromagnetic waves that they can be generated. And why we need them? Because these waves can scatter the electrons, and in that case they can do the, for example, the stochastic shock drift acceleration, or they can go back and gain energy. And this has to do with the temperature of the plasma in these regions. So we need to explore how the ion kinetic instabilities can be related to the SSDA process and can play an important role to the particle pre-acceleration. So here you can see the critical Mach number in 3 different cases for plasma beta equal to 1, because we want to compare our results to previous work with a hybrid code. And you can see that for a sonic Mach number 2.9, nothing interesting is happening here. This is the critical Mach number 3.5, where the ripple starts to appear. And of course, for higher Mach numbers, then everything is more interesting, and you can see the ripples here. And how we can calculate also the reflected part of ions in front of the shock, and see if we are above values that can define the critical Mach number. So it is smaller when we have sonic Mach number less than 3.5 in these parameters, and above the critical Mach number, then this ratio is higher. And another thing that we want to do, just to be sure that our results are good, it is to compare with the peak simulations. So here we have results for plasma beta equals to 5, and everything was in agreement with the peak simulations, which is very good. So we have the ripples, the reflected ions ratio, it's the same, the wavelength of the ripples, and this is very encouraging to us to continue our study. And here you can see also the profiles of the magnetic field and the density. And here is the anisotropy that I told you before for the temperature. This is the perpendicular and parallel temperature with respect to the local magnetic field. So you can see that the perpendicular temperature is higher than the parallel, and this is something that is happening and is triggering the alpha ion cyclotron instability. And now we did the same for many plasma beta to check if the general behavior is the same, which it is again something that we can see and see the ripples. In general, the structure more or less is the same. So it seems that the alpha ion cyclotron instability is important in the appearance of these ripples, and we can study then the generation of the electromagnetic waves. And also, apart from the simulations, if we have the opportunity to compare with analytical solutions, it's a good idea to do it. So here in Kim et al, they did a linear analysis for this instability, and as you can see, the wavelength from our simulation more or less is the same, and this is good. Also, according to our simulations, we found the critical Mach number for various plasma betas, which it's again an evidence where we should search for our results. And this brings me at the end. I hope that you are there and you're not very tired. The important thing is that now we use this hybrid code in order to investigate the ripplings in the shocks and see as the next step how they can affect the electron pre-acceleration in order to solve the injection problem that I described before. And thank you very much. Have καλό χειμώνα, μέρα που είναι.
Thank you very much, Stella. Clap for everyone present. So we do have time for a couple short questions. So if you want to ask something, please go ahead.
Stella, thank you for the talk. I learned quite a bit. I seem to have missed the main point, that is where what evidence do we have that the clusters of galaxies are sites of particle acceleration?
Because
And,
we,
yes.
no, sorry, continue, I'm sorry. Because we can see this radio and X-rays here. So in order to have this non-thermal emission, that means that we have a non-thermal population there. And here we have.
Why is that? Thermal electrons also produce radio.
It's the power law also that we have from the spectral distribution.
The spectrum.
Yes.
Well, even thermal electrons can produce power law radio spectra.
I don't have a one spectrum, but it is in a non-thermal regime to explain that we need to have, it is very steep, the power law that we need to have.
Okay, so I am not objecting that there may be non-thermal electrons. I only said that thermals can do it too, but that's okay. So so this is not then acceleration as you had in blazars.
No.
No, it's something different. It's a different problem.
Yes, exactly.
Okay, all right. So you're exploring what happens in shocks that are produced in clusters of galaxies.
Mm-hmm.
Okay, all right. Now I understand. Thank you. Thank you.
Stella, thank you very much. It was a very nice talk. It's one thing that we also observe is that, as Nikos said, we have a lot of thermal plasma present besides the acceleration of particles. So shocks do not accelerate, do not heat as efficiently the plasma. So the blobs that you are talking about is not a linear instability evolution. It's a much more complicated structures, coherent structures, which may be appearing stronger and stronger as the time passes and the shock dissolves itself. So I'm thinking that the strong turbulence, which the shock may be the generator of them, is a much more rich, much richer phenomenon that I think we have to move to the next step beyond the shock acceleration, which is almost the entire astrophysical community has been completely, robustly, locked in. I'm not agreeing with this because I think once the strong turbulence appearing in front or behind the shock, especially behind the shock, and a reconnection appears there, as we see in the heliosphere, in the shocks in the heliosphere, a new accelerator appears suddenly, which was not there in the initial setup that you've been analyzing of the simple shock injection and all that, which is very traditional and very old by that time, and 2D structures. We have the 3D structures also as well. So to close up, I feel that we have to move on from the shock to the next generation of strong turbulence, which have reconnections included, coherent structures included, and heating is a very interesting part of the whole process of dissipation of the energy, besides the power law acceleration, which may be there, depending on the total environment. I'm sorry for taking
No, I totally agree.
a big comment, but I think we are moving on. We have to leave the shock behind, and we have to discuss that in astrophysical environments, the shock is is an initiation probably. You know, it may start with a shock, but then after the time goes, the blobs, which you see, take over.
Mm-hmm.
They may dissolve it completely. The blobs remain. The blobs have reconnection. They have lots of interesting things that are much more interesting accelerators, in my opinion, than, and we see this in the heliosphere.
Yeah, I agree. I don't have something to say.
Okay. Thank you very much. It was have a nice Christmas yourself, and it was very, very interesting talk. Thank you very much.
Thank you a lot.
Sorry, I was muted. So any final question for our speaker? Well, if not, so thank you, Stella, for this very interesting talk. And thanks everyone for joining, and wish everyone a very festive season with your loved ones. And we'll see each other again next year. So bye, everyone.
Thank
Happy
you.
New Year to everyone.